Today, we are breaking down the absolute fundamentals of the universe's ultimate shapeshifter, energy. Specifically, the two forms that control every single moving part of our daily lives: potential energy and kinetic energy. Let's start with a simple definition. What is energy? In physics, energy is defined as the ability to do work, and work just means moving something against a force. But energy cannot be created from nothing, and it can't be destroyed. It can only change its outfit. The two most famous outfits it wears are potential, the energy of position or storage, and kinetic, the energy of motion. Let's look at potential energy (PE) first. Think of it as power on pause. It is energy stored within an object, not because it's doing something right now, but because of its position, its state, or its configuration. There isn't just one type of potential energy. Let's look at the big three. 1. Gravitational potential energy. This is the most common type you deal with. It depends entirely on how high up an object is and how heavy it is. The math behind it is beautifully simple. P equals mgh. M is the mass of the object, how heavy it is. G is the acceleration due to gravity on Earth. That's roughly 9.8 ms2. H is the height. Why this matters: if you lift a 10 kilograms bowling ball 1 meter off the ground, it has stored energy. If you lift it 10 meters high, it has 10 times the energy. The higher it goes, the more gravity wants to pull it back down, and the more energy it stores. Elastic potential energy. You don't have to lift something up to store energy. You can stretch it or compress it. Think of a rubber band, a trampoline, or a mechanical watch spring. When you distort the shape of an elastic material, it stores energy trying to snap back to its original form. 3. Chemical potential energy. This one is invisible, but massive. It's the energy stored in the chemical bonds holding molecules together. When you eat an apple, your body breaks those bonds down to fuel your muscles. When you put gasoline in a car, a spark plug releases that chemical potential energy in a controlled explosion to move the pistons. Now, what happens when you release the bowstring or let go of the bowling ball? That stored potential energy instantly transforms into kinetic energy, the energy of motion. If it's moving, it has kinetic energy. A soaring eagle, a spinning typhoon, a rushing river, and even the tiny, vibrating atoms making up your desk right now all possess kinetic energy. Unlike potential energy, kinetic energy doesn't care about height. It cares about two things: mass and velocity, speed. The formula looks like this: K equals rho(1 mov2). Notice something crucial here: velocity is squared v2. This means speed has a massive or disproportionate impact on how much kinetic energy an object has. The speed trap. Let's say you are driving a car at 30 kilometers per hour, and you suddenly double your speed to 60 kilometers per hour. Because velocity is squared in the equation to 2 equals 4, your car doesn't have twice the destructive kinetic energy, it has 4 times as much. This is exactly why high-speed car crashes are so vastly more dangerous than low-speed ones. The energy scales exponentially with speed. In the real world, these two energies are constantly trading places in a beautiful, mathematical dance. Together, they make up what physicists call total mechanical energy. X total equals P plus K $. In an ideal system without friction, this total number never changes. This is the law of conservation of energy.